Hi, Math 2. This is lesson 4 on page 31 of our workbooks, distance and circles. So today we are going to be using the distance formula, and we're also going to be learning the equation of a circle. So let's get ready to do that together. Going the distance. Andre says, I know that I can find the distance between 2 points in a plane by drawing a right triangle and using the Pythagorean theorem. But I'm not sure how to find the lengths of the legs of the triangle when I can't just count the squares. Explain to Andre how I can find the length of the legs of the triangle in the image and then calculate the distance between P and Q. So I'm going to actually do this two ways with you. The first way, we're going to look at using the Pythagorean theorem, very much like we did with lesson 3. And the second way, we're going to look at using the distance formula that you might remember from junior high. So let's get started with this right here. So unlike in lesson 3, we can't just count our squares, but we do know that this horizontal direction is the x direction. And here I'm at 8. And when I get over to here, this point right here, from P to N, I know that I'm at 53. So one of the ways to determine this distance right here is to find the difference between 53 and 8. So this distance is really 53 minus 8. And my vertical distance here, so I go from a y value of 12, and would have a y value of 12 because P has a y value of 12, up to a y value of 22. So my vertical change, my vertical distance would be 22 minus 12. That would tell me the distance between these 2 points. So if I did that subtraction, I'd find that my distance here is 10, and I'd find that my distance here is 45. So using our Pythagorean theorem, now that we've done that, if this is a right triangle, then PQ would be my C. It's my hypotenuse. It's across from my right angle. So it would be equal to 45 squared. That would be the straight horizontal side, plus 10 squared, this side, and that would be equal to PQ squared. So we would need to get out our calculators and square 45 and square 10, and we'd find that we get 2,125 equals PQ squared. To solve for PQ, I'm going to take the square root of both sides. The square root and the square cancel each other out. And then the square root of 2,125 is approximately 46.09. So I want to remind you of the distance formula, which is something that you probably used in junior high. Our distance formula was the square root of the difference in our x's between 2 points squared, plus the difference in our y's. And when I use the distance formula, it doesn't really matter which x I use first, and it doesn't really matter which y I use first, because I'm going to be squaring them in the end. So in this problem, our 2 points that we're using is 8, 12, and 53, 22. That's the distance I'd like to find. I'd like to find the distance between P and Q. So let's look at this distance formula. The distance is equal to the difference in my x terms. Well, interestingly enough, this is my x term and this is my x term. And it actually doesn't matter whether you start with the 53 or the 8. In the end, it doesn't matter because you square it. But I'm going to start with the 53 minus the 8 squared, plus the difference in my y values. My y values are the 12 and the 22. So I'd have 22 minus 12 squared. And I want to show you something. Up here, my horizontal direction was the difference in my two x values, 53 minus 8, just like it is in my formula. And it would be okay if it was 8 minus 53, because I'm going to square it. I don't really care if this number is negative inside my parentheses. And then look right here. I found my distance between Q and N by doing 22 minus 12? Well, that's also the difference in my y values. It's actually the same math. At this moment, what I have here is 45 squared plus 10 squared, just identical to what I have on the left side with the Pythagorean theorem. You might say, well, it's not the same. I have a square root symbol here. It is, because here I had my PQ squared, so then I took the square root of this side to solve, and over here it's just already done for me. It's all on one side. So I would get the same 2,125 when I calculate 45 squared and 10 squared on my calculator, and I would get the same 46.09 for my distance for PQ. And the fact that I have a D for distance, I'm talking about the distance between P and Q, so that's really the same thing. I do want to mention a common mistake that can happen on your calculators. So this is a separate, but a mistake that will often come up. If you started with the 8, for instance, in this term right here, and you had 8 minus 53 squared, that's just fine. When you do that, you get a negative number. You get the negative 45. 8 minus 53 gives me the negative 45. So here's what happens to students sometimes. Sometimes students will put the negative number into their calculator and then they'll square it. Notice what's going to happen here. When you square a negative number, you should get a positive answer because a negative times a negative is a positive. But when I do this, it gives me a negative 2,025, and that's because my calculator squared the 45 and then multiplied by this negative in front. It didn't square negative 45. One way around that is to make sure you put parentheses, make sure you put parentheses around your negative number before you square it, and then your calculator will give you the correct positive answer. So just something to keep a lookout for as you do problems. Okay, ladies and gentlemen, let's take a look at the next page, page 32. We're going to use the distance formula and the Pythagorean theorem inside of a problem with a circle. So it says this image shows a circle with the center 610 and the radius is 17 units. I'd like to remind you that means any point I pick on my circle is exactly 17 units away from the center of my circle. So anywhere I would draw in a radius would be exactly 17 units. So it says the point 1425 looks like it might be on the circle. So let's go mark that. 1425 would probably be right about in there. 1425. It looks like it possibly could be on my circle. It says verify if it's really on the circle. Explain or show your reasoning. So for me, I would tell you that I would use the distance formula. I would calculate the distance between 610 and 1425. However, I'm going to do number 1 using the Pythagorean theorem, much like we did here on the left side. And I'm going to do the second problem with the distance formula. That way you can see them both and then decide which one you might like to use. But I would like to mention that I think this is a great opportunity to use the distance formula. So I'd like to calculate this distance right here. I'm curious to see if it's equal to 17, which is what the radius is. So let's find that by creating a right triangle, if I'm going to use the Pythagorean theorem. And that means that I need to find a value for my vertical side and a value for my horizontal side. So I notice that my x-coordinate is 6, and I go over here to an x-coordinate of 14. So that means I went over 14 minus 6, or 8 units in the horizontal direction. Okay, so I was at 10 here, and I'm going to travel up to 25. So I'm at 10 on the y direction, on the y-axis, and I travel up to 25. So this distance is 25 minus 10, or 15. So I'm ready to do my Pythagorean theorem. I know that 8 squared plus 15 squared should be equal to, but I'm going to put a question mark, should be equal to 17 squared if this is really equal to the radius of 17. I don't know that yet. I'm trying to show that this is 17. If it is, then 1425 is on my circle because the distance between it and the center of my circle is equal to my circle's radius. So let's see if this is true. So 8 squared is 64 and 15 squared is 225, and I'm trying to see if that is equal to 17 squared. So let's go find our 17 squared. It's 289. Okay, so 64 plus 25, that is 289. So since my a squared plus b squared is equal to my c squared, then I know that this point, 1425, is on my circle because the distance between the center and the point was equal to 17, which is the radius. So what does it look like maybe if it's not on my circle? That's what we get to look at next. Let's check out this one, the point 22, 3. So let's come over here to 22 and go up 3. I'm going to do this in a different color. Let's say it's this point, 22, 3. Yeah, that looks like it could be on my circle. That's kind of a maybe. I think it looks possible, but we're going to use our math to prove it. It says verify if it's really on the circle. I'm going to do the same thing. I would like to see if the distance between my center and this point is equal to the radius of 17. Is that distance equal to 17? So this time I'm going to use the distance formula. So the 2 points are the center of my circle, 610, and the point on my circle, 22, 3. So let's bring over the distance formula from the previous page. It was the square root of the difference in my x's squared plus the difference in my y's squared. So it doesn't matter which number I use first, the 6 or the 22. I'm going to use the 6 first so you can see what it's like when it's a negative, but it doesn't matter. Plus, and now it doesn't matter if I use the 10 or the 3. In the distance formula, it doesn't matter. I'm going to use the 10 minus the 3. Those are my two y terms. So I have then 6 minus 22. Looks like it's negative 16 squared, plus 10 minus 3, 7 squared. That equals, now this is where if I'm going to square a negative 16, I need to make sure I put parentheses around it. Here, I'm just going to square. If I hit the squared button, it puts the negative 16 in there for me, and I get 256. So 256 plus 49. Let's see what that is. Okay, 256 plus 49 would be 305. And when I take the square root of 305, I get 17.5 approximately, and that is not equal to 17. This point is not on the circle. It's slightly outside the circle. It'd be somewhere out here. It's a little farther than 17 units. It's outside my circle then, because that's greater than 17. So this point is not on my circle. That's the point 22, 3. So let's take a look at this question. We're going to talk about this when you come to our Zoom office hours. In general, how can you check if a particular point, like our 1425 or our 22.3 or any point, is on the circle? How might I be able to check for that? What was I doing both in my work with the green and my work with the blue? I was trying to show that the distance between the point, we'll call it xy, and the center is equal to the radius. This is a really important part. And if it's not equal to the radius, if it's a number bigger, think about where that point would lie, because we're going to talk about that in a little bit. And if it's a number that's smaller, let's say I had gotten a 12, then where is that in relationship to my circle? Like, where would that point maybe lie on my graph? We're going to be talking about that a little bit later. Okay, ladies and gentlemen, so if you could please turn to page 34. This is the last activity that I'd like you to take notes on in this particular lesson. 4.3, building the equation of the circle. Since we're not in the classroom, I'm going to actually have you at the top write the equation of the circle, and in doing numbers 1 and 2, we're going to see how we use the equation of our circle. So this is brand new. It's kind of exciting. The equation of a circle is written the following way: x minus h squared plus y minus k squared equals r squared. So that's pretty fun. A lot of variables there. My x and y are exactly what they sound like. That's my x coordinate and that's my y coordinate of a point on my circle. The HK is the center of my circle, and the r is how I denote the radius. Keep in mind, and we're going to be talking in a minute, that the center is HK. And notice in my formula there's a negative sign here. You're going to have to use the same skill you guys used last year. This is a side note. But last year when we learned about parabolas in Math 1, we had an equation. Y equals A times x minus h squared plus k. You might remember this. And this term right here, when we'd come up with our h, we'd always have to do something called think the opposite to come up with it. And I'm going to be referring to that in just a little bit when we talk about these points as well. So let's take a look at this in a problem. This picture shows a circle with a center -3, 6, and the radius is 13. So it says write an equation that would allow you to test whether a particular point is on this circle. So in this one, if this is my center, if my center is -3, 6, remember that's my HK. So let's put that into my formula. So up above, I had x minus h, so x minus a -3. Squared. X minus a -3. A double negative is a positive. Negative, negative. So it's really x plus 3. Plus y minus 6 squared equals my radius squared. And in this case, that's 13. I want you to pause and take a look at this for a moment. So in this problem, this is actually an equation that represents this particular radius drawn right here. This is my center, -3, 6. This is a point, and this is a point on my circle, xy. And the distance between them has to be 13, because if this is on my circle, then it would be r units, the radius away from the center, which is 13. What does this look like here to you? Do you possibly see, dun, 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 our distance formula, the difference between x values and the difference between my y values squared? And in this case, you might say, well, I don't see a square root symbol. You're right about that. You don't see a square root symbol here, but that's because this 13 is squared on this side. So this is the equation of a circle. If you have the equation of a circle, you can check to see if any point is on it by simply plugging in that point. So it says use your equation to test whether 9, 1 is on the circle. So I'm going to use this equation by replacing my x with the 9 and the y with the 1, and I'm going to see if it makes this true. This is exactly what we were just doing a moment ago. if I could go back to this page, we were checking to see if the distance between the center and 1425 was equal to the radius of 17. Here we were checking to see if the distance between the center 610 and the point 22.223 was equal to the radius of 17. That's exactly what we're doing here. This is the equation of my circle. This is the distance between my 2 points. And I'm trying to see if that's going to be equal to my radius. The reason I don't have my square root symbol here is because both sides have been squared, and that's why I don't have to worry about that part of it. So let's plug that in. I'm going to put the 9 in for my x, and then that's plus 3 squared equals my y, which is 1. I'm not equals, I'm so sorry, that's plus. Y, which is 1, minus 6 squared. And I'm trying to see if it makes this true. Is that really equal to 13 squared? So let's check it out. 9 plus 3 is 12. I'm trying to see if 12 squared plus 1 minus 6 is negative 5 squared. And I'm trying to see if that's equal to 13 squared. So 12 squared is 144. Negative 5 squared is 25. And 13 squared is equal to 169. So now we're going to do 144 plus 25. I'll give you a moment to get out your calculators. And you should be getting 169. So 169 equal to 169. My 0.91 is on the circle. It made my equation true. If I would have plugged in the 9 and the 1, and I would have got another number, like 184. 184 does not equal 169. Therefore, the point would not have been on my circle. So on step 3, it says, suppose you have a circle with this center HK, and radius R. Write an equation that will allow you to test whether a particular point is on the circle. That's our equation of a circle. So let's write that down again. X minus h squared plus y minus k squared is equal to r squared. This is the distance between the center and the point. And technically there is a square root here. But when I square both sides to get rid of it, the square root goes away and I end up with r squared on the other side. So this is important to memorize, and one nice item in your locker that you could print out if you'd like, there is a Unit 6 equation sheet, and you'll notice that the very first equation on the equation sheet is this circle equation you and I just went over today. And then we're also going to be talking about parabolas. This is the parabola equation I mentioned from last year that we're going to be revisiting this year. And we're also going to be talking about lines. You might remember the slope-intercept form from before. The point-slope form you and I are going to learn in this unit. Slope equation from maybe junior high. Talking about parallel and perpendicular lines. The distance formula we also used today. So these are things that you and I are going to be using in this Unit 6. You could print this out or just use it as a reference when you need it from the locker. So ladies and gentlemen, that concludes our lesson 4. There is a summary you can read. The summary will again talk about finding distances. It will be talking about using the Pythagorean theorem to find this distance, but remember the Pythagorean theorem and the distance formula are really the same thing. And then they're talking about finding out if a point is on the circle. How can I figure out if a point is on my circle? So this would be a very good page to look at. And if you have questions, please bring them with you to our Zoom office hours. Thank you.